So this title that is really, let's say, common in the data quality part is born from the study of the data quality dimension. But before to introduce this part, I would like to start from the background, so where this research started. So the research starts from my PhD, where I proposed a hierarchical use of shared environment, and where the point about the translation of models, and with models I intend all the data, all the information that runs around the models in terms of development of the models with beam authoring tools are translated one point from the other. The point about data quality become really important because the use of the model, the use of the data is really focused on the quality of the input data in the different stage. And starting from this point, so starting from this need, the idea was to start studying the data quality dimension from the information technology department, so starting from this definition and this part. So about the title, Real World Data is Dirty, is a phrase from a well-known paper in 1998 that is focusing on the data quality dimension in the IT field. But what means that data are dirty? So data dirty means that we have missing data, or we have wrong data, or we have not standard representation of data. And this in BIM is something that is really not that easy to understand, what is a not standard representation, for example, of a data. But then on the other hand, we have also another really important definition about data quality, that is data quality means data that are fit for the use by data consumers. And this is really important when we talk about BIM, because I will return on this point in a moment, but when we talk about the development of the model, we have to think about what are the needs and the use of the people that are developing the model. So I found a paper that I used to focus my research in this case about the classification of the concept of data quality for BIM. And the data quality in building information modeling can be divided in different parts. So we can have the process quality, so the quality of the entire process. Then we may have the quality of the model, and the quality of the model can be identified as the quality of the model as an overall quality, so making, for example, clash detection and everything else to have a good project, let's say, or the quality of the object composing the model, so the quality of the information, all the information inside of the model. And in this case, this research is focused on this point, so it's not focused on developing the a quality framework for the entire model or for the process, but to understand the data quality dimension inside of the object for the model. Coming back to the definition of data quality, so the quality that fit for the use of the consumers, the point is that in many cases, in the majority of the case, the models are developed during the design phase, are developing during the construction phase, but are developing by people that have as, let's say, has objective the definition of the project, the construction of the building, but usually are not focused on the future use of the data. Many times we fix this problem defining stricting rules, defining standard, and imposing the use of specific information, specific standard for the development of the model. But as we, for example, seen in the presentation of this morning about semantic enrichment, we know that we need to, in some way, help the introduction of information inside of the model to allow, for example, code checking definition, to allow the development of specific use of the models according to the data that are included in this model. So we have to know the importance of the quality that we have in the model, because if we know the starting point about the quality, we can also develop different algorithms, for example, for code checking, or different algorithms for semantic enrichment that can take into account problems that are critical in the starting point. There are several research about the use of the data quality in terms of, for example, translation from the native model to the IFC, then from the IFC and opening the IFC standard with a software. So all this kind of quality issue, but I didn't found many studies about the quality of the starting model, so the quality of the model in the native format. And here the paper is focused on this, so on the study of real-world building information models developed using a specific software to understand if we have, let's say, common mistakes in different models that can be categorized and that can be used to improve the future algorithm. So here is the method that we use. So we defined in a competitive tender for a common, let's say, employer information requirements. So the rules were the same for everyone, the objective were the same for everyone, and we selected 4 project team to develop the model. So the project team defined a BIM execution plan as an answer to the employer information requirement, and every team defined several building information models to define the design. So we took this building information model and we use specific dimension for the data quality to evaluate common mistakes or common issue, let's say, inside of these building information models. About the data quality dimension, in the literature can be found a different definition, at least 1,000 of dimensions to evaluate data quality. These, in the information technology field, are the most common use dimension for data quality that are accuracy, consistency, completeness, and timeliness. In the case of timeliness, we were not able to use these because the model were statics, so we are not able to define a quality dimension about the evolution of the data on these models. And in addition to these 4 dimensions, at least to the 3 dimensions that we used, there is another dimension of data quality that, let's say, it's null value. So in database, it's a common issue, the presence of null values, because it's really difficult to understand if the values is null because someone forget to put the value, or because it has to be null, or because, I don't know, for other reasons. So it's not easy to evaluate null values. And as we will see, in building information model, usually we have tons of null values that we don't know how to use in the evaluation process. So about accuracy, so we took these models and we start to evaluate manually and with algorithm the composition of these models, so these different models. And about accuracy, for example, we have different type of issue related to data quality that can be classified. Of course, the classification that I propose here is not a final classification, but it's just a starting point to try to identify common issue that sometimes are also software related, but that can be used if I know the software from which my model arrives. If I knew the issue, I can fix my algorithm to, in some way, limit the impact of this issue on my final results. So in this case, for example, for accuracy, we have inconsistency between information fields, because many times people put different information in the names of the object inside of the model, and these information are in contrast with the other information that you have. For example, the thickness of the wall, you have it in the name, and then also as information of the object. Or for example, human-related accuracy issue like typos or other problem like this, or pre-compiled information fields, because many times, in this case, the model were developed using Revit, you have several information fields that cannot be deleted in the model, but are never used by the users, or in some cases are already compiled by the software and no one change it. So anytime you have this data, okay, anytime you have this data that you cannot use. About consistency, we have the misuse of BIM object categories. For example, we have walls used to model everything in the building, from skirting to pillars to everything else. So also in this case, we cannot use the classification of the semantic structure of the building information model to identify the object, or at least not for all the object. Or for example, not coherent use of the same information field. So also in this case, the same information field used for different information. And about completeness, in this case, the requirement was to use the American law, the 300, and here there is the comparison between the requirements of the USA BIM forum and what we found in the model, so the number of information field that we found in the model. So no one of the models satisfied the USA BIM forum, and this can be related also to the use of something that is from USA in Italy, but this is another discussion. But the interesting point also is that we analyzed some object, but every different models to obtain the same results, that was what we defined in the employer information requirement, define different several information fields inside of the building information model. So modifying the semantic structure of the building information model and removing de facto what is the shared information structure that we have. So every model in the delta, you can find how many information fields each model add to the, for example, to the walls, to the windows, or to the pillars to represent and to satisfy the objective. And what we found at the end is that if we, what's happened? Let me come back. This one, okay.
Go back. Yes.
Okay. If we look at the percentage of empty field that we have, for example, Model 2 have 52.4% of the field filled, and the other 38% empty fields, so null values. So a lot, and if we look at the number, 90K of information field, you may understand how many information fields we have, and we don't know how to do with these information fields. So at the end, to conclude the presentation, what we have done, so we took 4 information model, in this case, several information model, but we took in the project 4 design with building information models, and we analyzed these information models using data quality dimension to highlight common mistakes or common issue related to data quality. Why we have done it is because in the literature we have found several experiments using, for example, the data inside of the information models, and one common line in the discussion of this paper is that the data quality of the input data is really a critical issue in the final result of these algorithms. But if we will be able to, in some way, classify this issue and identify common issue in different models, we will be also able to improve the existing algorithm to fix this issue, or at least to limit the issue that we have. As a future works, what we would like to do is to repeat this experiment using other building information modeling tools for the development, so not Revit, but for example, Allplan, Graphisoft, and so on, and to maybe try to have the same experiment in a different cultural environment, so not in Italy, but maybe in another country, to identify if the issue are related to the behavior of the people that developed the models in the country, or if these issues are related to the use of the instrument or to the use of the implementation of the building information modeling as a process. So that's it. Thank you.
Thank you. Thank you very much. Okay. So it's a very thought-provocative presentation. It triggers some comments, questions. So please ask Claudio now.